hazards. Is your company in compliance? And this presentation was originally developed for the United States. It primarily refers to U.S. standards, but I believe it will be of interest to people throughout the world. The outline is given on the second page, and this gives the basic contents that we're going to cover here. First of all, we're going to look at electrical safety in general and some of the general considerations that have to be addressed when you have any type of electrical safety program, and of which arc flash is one part. Then we're going to talk about the risks of arc flashes and the effects that are caused by arc flash, both in terms of human injury and death and equipment damage. Then we're going to talk about the various approach boundaries that have been defined, which are necessary to observe depending on your level of qualification and the amount of personal protective gear which you are wearing. There are also approach boundaries for electrical shock that will also be discussed. There are two main ways of calculating arc flash hazards. The NFPA 70E, that's the National Fire Protection Association, publishes a guide, and NFPA is the also the publisher of the National Electrical Code, which is used in the United States. And second of all, there is the IEEE standard 1584, which gives calculation procedures for arc flash hazards that were derived from a series of tests. So these are empirical equations based upon experiment, and in fact that standard is undergoing revision as another series of tests is taking place as we speak. Now, when you have an arc flash hazard, there's two basic things you can do. You can do remediation to reduce the hazard, and you can also wear protective clothing to protect yourself against the hazard. And there are also labels which are required to be placed on equipment where arc flash hazards exist, and we'll discuss those and show some examples. And then there are also work permits which need to be issued when people are performing work involving arc flash hazards. And again, these are based on the regulations in the United States, and they may be different in other countries, but it gives a good overview of the field. So the first thing to recognize is that worker safety is of primary importance, and we don't want to compromise the safety of people working on electrical equipment. And in addition to being the right thing to do, worker safety is connected with productivity, worker morale, and liability. For example, when you have an accident, you do lose production time, and it does make other workers more nervous and develop negative attitudes, which is not good. And there is also always the liability issue in that workmen's compensation cases and lawsuits can come out of worker injuries. Okay, so the important thing is to design the machinery, the processes, the systems, the facilities should be designed with safety as a key consideration from the beginning of the design phase. You should not consider safety at the end of the design. Okay, now we've designed a system, now how do we make it safe? You think about safety from the beginning when you are designing an electrical system, so that you consider that when starting from laying out the single line diagram to selecting the equipment, determining the operating modes, the whole process has to take safety into consideration. In fact, there is now a standard in the United States and Canada on implementing electrical safety programs in facilities, so that there are procedures given within ANSI Z10 for providing procedures for improvement of occupational safety and health. There's a hierarchy of control measures, and you notice what people mostly discuss regarding arc flash hazards is PPE, personal protective equipment, and you'll notice that's the last thing on the list. The first thing to do is to eliminate the hazard if possible, or if you can't eliminate it, substitute a less hazardous equipment for what was being proposed. Then there are engineering controls to reduce the exposure to hazards and the severity of hazards. Then there are warning signs, and then there are administrative controls, including safe work practices. And finally, the PPE. And it gives, for example, a maintenance switch is a common way of reducing arc flash hazard. This is a switch which changes the protection settings on your switchgear from, for example, time delay to instantaneous trip while you are working on the equipment. That's an administrative procedure, and it depends upon the maintenance switch working and people using it. On the other hand, if you use less hazardous equipment or engineering controls, for example, you can put in zone selective interlocking, which is a means of having a fast trip on a circuit breaker automatically, or you can put in, for example, arc-resistant switchgear, which diverts the effects of any explosion or arcing away from a person standing in front of the switchgear. So there's a whole range of approaches here, and the idea is always to make a facility as intrinsically safe as possible. But the only true way to work on an electrical system safely is when it is de-energized. And this involves the lockout-tagout process and grounding of the formerly energized conductors that you are going to be working on. That is the best way. However, it's not often possible to do that because of critical industrial processes which have to run 24/7. And in some cases, there are redundant systems involved. For example, alternate feeds or double-ended substations that will allow you to completely isolate one piece of equipment while still running the process. And then you can also look at, as I said, less hazardous equipment that has a lower level of risk. For example, individually mounted breakers instead of mounted all in a group, or you can have draw-out circuit breakers instead of bolted-in circuit breakers so that you can remove the circuit breaker to work on it on a bench not connected to the equipment. And of course, arc-resistant equipment I mentioned, and then there is indoor versus outdoor equipment, and regarding that, I think that okay, indoor equipment may be safer to work on in terms of you having more space to work and not being in a metal box where you're working. And then you can also do design and instrumentation and monitoring so that you can do as much as possible remotely. You can, instead of walking around with a clipboard and writing down meter readings as has been done in the past, now you can stay in your office and get all the meter readings on your computer. And for example, instead of unracking a draw-out breaker with a hand crank, now that you can attach a motorized unracking device and operate that remotely from a distance so that you don't have to be standing in front of the breaker if something fails while it is being unracked. So the general hazards involved in working on or near electrical equipment, we talk a lot about arc flash, but there's really a lot more hazards than just that. Of course, electrical shock is when you come in contact with an energized conductor and then electrical current flows through your body, and then you have become part of the circuit, and this is often fatal. and should be avoided at all costs. Arc flash, the violent release of hot gases caused by an electric arc, where an electric arc can be caused by insulation failure, a short circuit, say if you're racking a breaker in and out and contacts aren't lining up correctly, if somebody leaves a tool inside a piece of equipment and then it's energized. There are many reasons for short circuits and other types of failures that will cause an arc flash, such as, for example, if a circuit breaker is attempting to interrupt a higher fault current than it's rated for, then the arc is not interrupted when the breaker is open, and you have another arc flash situation. Now, when you get these superheated gases, which can expand, for example, copper expands something like 64 million times in volume from copper solid to copper vapor at a high temperature. This causes a pressure wave and a blast, and this is why that you always need to wear hearing protection as part of your protective gear. Shrapnel, when you have this explosion, then you will have pieces of circuit breaker, you will have doors blowing off of switchgear compartments, and various other projectiles that can damage you just like a bullet. So for higher levels of arc flash protection, the protective clothing actually is padded and may contain bulletproof type material to protect you against that. And then of course there is the noise from the expansion of the air, which will be also a substantial hazard, as I mentioned. So if an electrical incident does occur, there are many possible ways in which people can be injured. So you need to try to, first of all, avoid having any of these effects happen, and if they do happen, you need to be protected against them. Now, NFPA 70E, that is the standard for electrical safety in the workplace. This has been basically adopted by the OSHA, Occupational Safety and Health Administration in the United States, and is also recognized in the National Electrical Code, which is the guide to performing electrical installations in the United States. And this requires that electrical equipment be marked to warn qualified personnel of potential electrical arc flash hazards. So it will tell you a sign that is put on the equipment, usually as a result of an arc flash hazard analysis by an engineer, which will tell you what the danger is and what type of personal protective equipment you should wear if you are working on this equipment while it's energized. And also, safety training is required. for qualified persons who are working on equipment. And this safety training is not a 1 hour webinar like this. It's a full day course with an examination given at the end. And that is something that I have been teaching that for a number of years at various industrial facilities in our area. And it's a very thorough course that involves not just talking but also demonstrations of the equipment which is being used. So this next slide is a statement of how OSHA incorporates NFPA 70E into its regulations. Now, the situation being that the National Fire Protection Association is a private organization made up of representatives from industry who get together and write a consensus standard. So this is similar to standards that are put out by the IEEE or the IEC. And as such, it is not a law or a government document. However, what the U.S. government is saying is that they are expecting that the users will be following the industry consensus standards regarding safety. And if it's found that, for example, they were violating the requirements of NFPA 70E, they could be cited for negligence if a incident occurred. And this can include various types of fines and other legal penalties. So the employer will use a consensus standard to decide how to design and maintain their electrical equipment, and the government officials will use the standard to see if the employer has taken proper actions to protect employee safety. Now, as things go, the latest edition of the standard is 2009, and the OSHA and other government agencies usually take a while to evaluate a standard, so they're usually at least one edition behind in their official written rules. However, as new requirements and improved practices come along, it behooves the user to adopt these when they become available, and not wait for the government bodies to review them and come to some conclusion about them. Okay, now we're going to try and talk about some more of the specifics. So this slide shows an example of an arc flash hazard incident, and in this case a person is using a volt-ohm meter inside a generator accessory cabinet to check some voltages on a 480 volt terminal board. So they placed 1 meter lead on one phase and use the other meter lead to check the other two phases. And what happened when doing that is that an arc flash occurred and the employee was burned. And in this case, it was not severe, so they were able to return to work. And it was determined that the terminal lugs were too long and that they were not insulated. So also that the meter being used had clamps that were too large for this type of equipment. So that basically there were two things wrong here. The terminal board had the incorrect lugs, and the person doing the measurement used the wrong type of probes to do the measurement. So again, when doing any work with energized equipment, it's very important to inspect the equipment that you're going to be measuring on to make sure that it is set up so that you can actually do the measurement safely, and to use the proper test equipment and probes. So in this case, this would have involved not doing the measurements right away, but you'd have to shut down the equipment, make some changes to the terminal boards, and go get yourself the right probes for your meter, and then come back and probably do the measurements the next day. The next example shows a metering compartment. This is a bank of electric meters, such as may be used in an apartment building to measure the power usage of each different apartment unit. And you can see here that there was a major explosion that destroyed several meters and blackened the paint surface all around. And on the next page, you see the workers' flame-resistant shirt and insulating gloves, and you can see that the shirt was actually burnt through, and that the gloves were also damaged, so that the workers' hands were burned as well. So this, despite wearing what was advertised as flame-resistant clothing and wearing insulating gloves, the worker was still not protected. And it says also that another cause of this failure was that there was a slow protective device. That is, once the fault occurred, it lasted maybe for several seconds. It did not have an instantaneous trip device. It might have had a slow-acting fuse that was providing the protection. So it shows that work needs to be done at a place like that to improve their protection system and to require the proper protective equipment for the people doing the work. Now, the temperature in an arc flash can reach 35,000 degrees Fahrenheit, and that's about 4 times the temperature of the sun. Now, we can convert that into Celsius. Just a minute here. Unit conversion number. I'm looking at my calculator here. Fahrenheit to Celsius. Okay, this would be 19,427 degrees Celsius. So either way you look at it, it's very severe temperature that will destroy anything in its path. In the United States, there are 5 to 10 arc flash incidents every day that require hospitalization, and 1 to 2 deaths every day, resulting in more than 2,000 workers a year being treated in burn centers with severe arc flash injuries. And those are just the reported incidents. And we know with all statistics like this that the number of unreported incidents is probably greater than the number of reported incidences. And in my particular company, I know an engineer who was hospitalized for an arc flash incident. He was drilling a hole in a panel in 480 volt switchgear, and there was a cable on the other side of the panel which was not de-energized. So you can see there was two things that he did wrong. First of all, he did not de-energize everything when he did his lockout, tagout, and applying of safety grounds. And second of all, he didn't look carefully enough behind where he was drilling to see that there was in fact a cable there. So this actually occurred in the switchgear room of a hospital. So he was severely burned, and as you may know, the doctors and nurses in a hospital are not emergency medical technicians. They're not trained to carry people on stretchers to the emergency room and apply, first aid and so forth. So they're trained to treat them after they've arrived at the emergency room. So they had to get an ambulance crew out there and bring this fellow from the switchgear room to the emergency room. And then it turned out this hospital did not have a burn treatment unit, so they had to ship him from Albany, New York to Syracuse, New York, which is about a 2 or 3 hour drive to a hospital that had a burn unit. And then he was treated there for several months. It's a very time-consuming and extremely painful treatment. But now he is recovered, and you don't even see the scars anymore, even though his face and his arm and hand were severely burned. But it's not an experience that anybody would want to go through. Okay, activities which involve arc flash risks are racking in or drawing out of circuit breakers, and second of all, removing or installing circuit breakers or fuses. For example, if you're going to change a fuse, you should de-energize the circuit before you change the fuse. You should not change the fuse on a live circuit. And I know in the past, many people, including myself, have racked out circuit breakers and have replaced fuses in live circuits, and that is not encouraged anymore. In fact, this is something that is extremely dangerous. If you do it while it's live, you have to wear a high level of protective gear. In fact, the worker shown in the picture in this slide is not wearing sufficient protective gear for what he is doing, And we'll show in a few slides later exactly what gear is needed. Now, if you're working on control circuits are normally low voltage and low current, like 120 volts and less than 5 amperes. But you'll have a control power transformer that may be connected to high voltage, and so that means that you have to treat the circuit as a high voltage electrical hazard and take the appropriate precautions and wear the right protective equipment. Ideally, of course, they can design control circuits such that the control power transformer is behind a metal barrier that would prevent any arc from hurting somebody working on the low voltage circuit. Applying safety grounds is, of course, critical in making an electrically safe work area so that you are not exposed to arc flash hazards, but while the grounds are being exposed, being attached, even though you have de-energized the circuit, you have checked for 0 voltage, you have to assume when you're putting the grounds on that the circuit could be live. There might have been some source of voltage that you missed, or somebody turned on some switch, they cut a bolt that you had locked out and turned it back on again. So you have to take extreme caution when applying safety grounds. Another thing is removing panel covers for inspections and other activities. Now, for example, I do power system studies most of the time, and I need to know what are the sizes of cables going to circuit breakers, and I need to know what are the settings on the circuit breakers. And in many cases, there's no way of finding that out without removing a panel or opening a door. And this involves a arc flash hazard. So the appropriate protective equipment has to be worn, or else the equipment has to be de-energized and grounded before doing that activity. And finally, low voltage testing and diagnostics. Now you're talking here low voltage circuits, say 480 volts, 600 volts, in that range. And in the past, again, people have treated these circuits rather lightly and just gone around clamping ammeters on cables and measuring voltage with voltage probes, but in actual fact, it can be extremely hazardous, especially if you consider, for example, that your clamp-on ammeter has an iron core which is exposed while it's open as you're clamping it on, which could draw an arc from some live part. So your safety precautions have to be followed in that case as well. So when you're doing this work, before you have an arc flash study done and labels, then you want to know, okay, what protective gear should I wear? What precautions should I take? And in the standard NFPA 70E in the United States, and there's a similar standard in Canada, there is a table which lists all types of electrical equipment and all types of activities which you can do, from anywhere from, reading a meter to withdrawing a wrecked-in circuit breaker, switching a switch with the doors open or switching a switch with the doors closed. It's a very detailed list, and it tells you the minimum protective gear that you should wear when doing any of these tasks on any of these equipment. Now, in these tables don't apply in all circumstances, and they are based on assumed data, of course, typical data for the industry in terms of available short circuit current and tripping times of circuit breakers and fuses. So if you need to know more exactly, if your situation doesn't match the tables, you need to do a arc flash calculation, and the procedures for that are listed in IEEE Standard 1584, the Guide for Performing Arc Flash Hazard Calculations, and this contains a number of equations which were derived empirically from tests that were done in short circuit laboratories of creating arc flashes and measuring with a calorimeter at different distances how much heat was generated. And these tests are being continued, and more different situations are being considered. The original tests were only for three-phase AC for voltages within a certain ranges, and now they're looking at single-phase and more different voltage ranges, and they're also, I believe, going to look at direct current as well. So there will be a new edition of 1584 coming out with that will be applicable in even more areas. So meanwhile, we work with what we have. Okay, how am I doing on? I just have 10 minutes left, I guess. So I'll go fairly quickly through some of these. This slide shows the various boundaries that exist around an energized part, and there are both arc flash hazard boundaries and there are electrical shock protection boundaries. And the next page shows a shock protection boundary, and there is a limited approach distance. This is entirely based upon the voltage from that's the distance within which there is a shock hazard. Then there's a restricted approach distance where if you're actually working on something, there could be an inadvertent movement, or one of a tool that's in your hand might touch some live part. And then there's a prohibited approach boundary, which is very short, just a few inches, which is considered the same as making contact with the live part. That is, if you have some conductive object that distance from a live part, you draw an arc right to it, and you might as well be touching it. And for arc flash protection, there are two boundaries. The first one is the flash protection boundary, and this is the distance where a person could receive a second-degree burn if there was an arc flash occurring. And this is considered to be 5 joules per square centimeter or 1.2 calories per square centimeter. And within this distance, you need to wear the personal protective equipment. And then there is the working distance, which is the distance at which we calculate what type of PPE you need to wear based on the voltage and how far away you might be from the energized part to do some work. Okay, that is, at higher voltages, you're probably going to be using a hot stick, whereas at lower voltages, 18 inches is considered to be the length of somebody's arm. Okay. What happened to my slide here?
Yeah, Peter. I don't know whether the conversion of this webinar platform missed one of the images. What is lacking?
Yeah, I'm not seeing any images. I'm just seeing the page number down at the bottom. Are you seeing the images?
No. In this page, no. In page 22, there is no image. So I'm afraid this is not possible to put it on the screen right now. So, well, maybe we should afford without it, and
Okay.
the audience will have this available in the version that we will put online.
Yeah, you can put it online. I'll just talk through some of these things then.
Yeah. So in the meanwhile, I invite you to proceed with the presentation by just skipping this part in this case.
Okay. So anyway, what we would have on page 21 is a distinction between what unqualified persons can do is stay outside of the limited approach boundary or the flash protection boundary, whichever is greater. Whereas a qualified person can cross the restricted approach boundary as long as that they have a documented work plan and they have the personal protective equipment. They don't go within the prohibited space. So a qualified person can cross the restricted approach boundary. And the prohibited approach boundary, which is the same as touching live equipment, is only for people who are trained to work on energized parts. And I know in many electric utility companies, they have people who are trained to do what's called live line work, where they can work on energized equipment. But if you don't have that type of training, you should not do that. Okay. Page 23 shows some definitions. The incident energy is the amount of energy on a surface a certain distance from a source of heat generated during an arc flash. And it's measured in either joules or calories per square centimeter, where 1 joule per square centimeter is 0.24 calories per square centimeter. So that we talk of, for example, either 1.2 calories per square centimeter or 5 joules per square centimeter as the limit. Arc flash hazard analysis is a calculation procedure to determine the risk of injury from arc flash hazards. The voltage fault current is what you calculate during a short circuit study. It's the amount of short circuit current that occurs if you have a zero resistance short circuit, like if two energized conductors come in contact with each other. Whereas an arcing fault current is if the two conductors do not come in contact with each other and there is an arc through an insulating medium in between them. And this is what is considered during an arc flash hazard analysis. We calculate the voltage fault currents, and then from that we can calculate what the arcing fault current is in that situation. And then the arc duration is simply the time that it takes for the protective equipment, fuses, and circuit breakers to clear the arc, to clear the arcing fault. So then the next, okay, now I got my slides back. Okay, I'm going to see if I can advance. Okay, I don't see how I can advance the slide right now.
Can I help you, Peter?
Yes, yes. Now I reloaded the system on the computer, and now I have page 22 showing, but I don't see how to advance the slide. Oh, here it is. Okay, I got it. Now I'm on page, I see page 24.
Yeah, indeed. Thank you.
Good. Are you able to see the slides now?
Yes, it works.
Good. Okay, I just had to reload it. I did a refresh of Internet Explorer. Okay, so slide 24 gives the responsibilities of the company which is owning the electrical equipment. For example, if you have, say, a cement mill or a paper mill, okay, it's the responsibility of the owners of that mill to do these things, to have an arc flash analysis of the power system, to establish the protective boundaries and incident energy levels, and put warning labels on equipment. Now, these three steps, they usually do this by hiring an outside consultant rather than doing themselves. A consulting firm that perform power system studies such as short circuit studies, coordination studies, load flow studies, and so forth. Most of them also do arc flash studies as well. And they will analyze the system and print up warning labels and put them on. Then the company also has to have electrical safety training for both the qualified workers and for the general workers. That is, workers who are not electrical workers, but they may be exposed to electrical equipment in their work, and provide the necessary personal protective equipment, arc flash suits, and so forth. And the same things apply if they use outside contractors to do work within their plant. Okay, the arc flash hazard analysis is sort of an extension of what you would do in a short circuit and protective device coordination study. You collect the data, you determine the system modes of operation, that is, you might have a double-ended substation that is operated either with the tie open and both mains closed, or with the tie closed and one main open and one main closed, for example. Or you could have situations if you have generation where you're powered by in-plant generators or where you're powered by utility power. Various modes of operation. You have to consider them all in your analysis. Determine the bolted fault currents. That's what's done during the short circuit study. Then determine the arcing fault currents. These are lower than the bolted fault currents. They're done based on what the voltage level is. There's going to be a certain amount of arc resistance occurring that will limit the fault currents. And then you have to determine the protective device characteristics and compare them with the arcing fault currents and see how long the protective devices take to operate during this case, which will be longer than during a bolted fault. Then looking at the system voltage levels and the types of equipment you have, you select the working distances, and then using the arcing fault currents and arc durations, and the working distances, you can calculate the incident energies and the arc flash protection boundaries. And these last three things here, the working distance, incident energy, and arc flash protection boundaries, these go onto the warning labels that are going to be placed on the equipment. Now, the next slide just shows different ways of doing the arc flash analysis. You can either look it up in tables in NFPA 70E, which is the least accurate way of doing this, or there are spreadsheets available. For example, IEEE 1584 comes with some spreadsheets that you can use to do the analysis. But the most detailed and accurate is to use Power System Analysis software, which is designed to follow the calculation procedures in the standard and is based on a complete system model that you develop when you collect the data. And so typically a program that does short circuit protective device coordination and other types of analysis will have a module that does arc flash also. And some of these programs will also print the labels out for you and the restricted work authorizations. And it's recommended that before doing the arc flash hazard analysis, you do a short circuit and protective device coordination study so that you know what the short circuit currents are and what the arcing fault durations are going to be. And then typically what you do is you go back, if you find some of your arc flash hazards are too high, you go back and revisit your coordination study, and you can adjust some of the tripping times of the protective devices. And that way you can make the reduce the arc flash hazards and hopefully still maintain coordination. And sometimes you end up not being able to prevent the arc flash hazards without totally doing away with protective device coordination, which is also not a good thing. So there's a balancing act that's involved here. And sometimes if you put in more modern protective equipment, you can avoid that problem. So here, the next few slides talk about product-based solutions. That is, okay, we're not just going to put labels on things and wear personal protective equipment. We're going to improve our power system by putting in devices that will reduce the hazards or eliminate the hazards. And I mentioned remote diagnostics and whereas your meters and controls can be located in another room, and you can do condition-based maintenance that if you can develop a probability that a piece of equipment might fail, then you can proactively go in there and do some maintenance and make sure your equipment is then in good shape so that you're less likely to have a fault. And you can use faster and more sensitive protective equipment such as zone selective interlocking, bus differential protection, faster circuit breakers, smaller fuse, and some of the newer circuit breakers have instantaneous protection which can be actually coordinated. So you can coordinate the instantaneous trips between two circuit breakers so that instead of having to have one circuit breaker on instantaneous, the next one on short time, you can have them both on instantaneous, but based on the I squared T let-through energy of the upstream breaker, you can coordinate, of the downstream breaker, you can coordinate with the upstream breaker. And you can also use light sensing to generate a trip that is putting in photocells in the equipment compartments so that if an arc develops, it will sense the light from the arc and cause an immediate trip, maybe before the arcing current was enough to trip a device based on current alone. Or it can be set so that it has to measure a certain amount of increase in current before it will trip on light to avoid a false trip, such as, say, if somebody opened an equipment door and light came in, and that's not an arc flash. So, yeah, there's lots of new technology out there to reduce arc flash hazards. In addition, you can use equipment such as arc-resistant switchgear, which diverts the hot gases from the arc flash up through chutes in the top of the equipment and outside of the room that you're in, maybe outside of the building, so that you're not exposed to the arc flash nearly so much. But that only works if the doors and panels are all closed, of course. You can also have active arc flash prevention by having crowbars, which places a dead short circuit and shorts out the arc. Of course, this might cause additional damage. And then I'm also going to talk about what's called an arc vault, which is a improved version of that method that actually transfers the arc to a sealed chamber. You can also use maintenance settings on your protection so that you reduce the amount of current that it takes to trip. when you are doing maintenance. So say you can throw a switch and set everything to trip on minimum pickup of instantaneous rather than what its previous settings was, and that way you will be much safer if you have to work on the live equipment. And okay, the next one talks about remote controls, metering diagnostics, and I think that I have discussed most of this already. So you can use the information to minimize the need to actually access the equipment in person, and including racking out of circuit breakers can be done automatically with a remote racking. This slide just gives a little bit more detail about the high-speed protection I was talking about, the zone selective interlocking, and basically what this does is if it looks at the fault location, and if the fault is outside down a feeder, then the feeder breaker will trip fastest, and then the main breaker will be backup. If it detects that the fault is in the switchgear, such that you have a fault current coming in the main breaker but no fault current going out the feeder breaker, then you change the settings on the main breaker to lower settings so that it trips faster. So that it can either be a backup or primary protection depending on the fault location. And bus differential protection in the past was normally used just for medium voltage buses using dedicated relays that had a current transformer on each feeder. Now, with low voltage switchgear having a single processor controlling the entire lineup in the newer designs, you can then implement bus differential protection as well as zone selective interlocking in low voltage equipment, which greatly increases the safety of that. And then the other things it talks about, I already mentioned, instantaneous selectivity, and their waveform recognition allows the breaker to recognize a fault even before the fault current exceeds the time of an instantaneous trip, so that it can say, okay, this is going to be an instantaneous trip, so we'll trip right away based on the waveform, rather than waiting for the current to reach so many amperes. And then you have your arc flash light sensitive relays, and it says careful with low voltage implementations. And what that means is in low voltage equipment you have air circuit breakers in a lot of cases, not vacuum or SF6. So these normally have arcs when they open anyway. And so there might be a false indication of an arc flash when it was just normal arcing that was safe. And also sometimes the doors don't seal tightly and there's light coming in from outside. So you have to be a little bit more careful with the light sensing. Okay, the next page shows some examples of remote controls. It shows a picture of a remote racking device that can be installed on a breaker, and how you can control switch gear without walking up to the front of the switchgear and operating switch handles, but you can do it remotely. And the next page shows arc resistant gear, and there's a couple things. Okay, this is a solution for people who are operating the equipment, but not if you're doing maintenance and opening any panels or doors, because it basically has a smokestack and sends out the arcing products, and it has to be exhausted and not just let loose in the room, which isn't going to be a solution. So arc-resistant switchgear is pretty common nowadays, and a new device that has just come out is an arc diversion that transfers the arc energy to an alternate current path. And okay, the most common implementation is a crowbar that just short circuits the arc, and this, however, can cause equipment damage and is probably not always reusable. So there has been a new device developed called the ArcVault, which instead of being a crowbar is actually got three terminals, one from each phase, and it has a igniter, which is basically, it's similar to the electric igniter on a gas stove, for example, so that if it detects an arc fault, it will trigger an arc within that container, shorting out the arc fault and containing the energy within that container. And it is capable of multiple uses. It is maintainable. It does have vents, for the arcing products to go out through the ceiling, but it's very fast, is compact, and does not cause damage like a crowbar does, because it's actually got an arcing current flowing through it, not a bolted fault current. Okay. The next one is, temporary instantaneous protection. Again, this is your putting in a maintenance switch and make sure that people are using it. But let me just skip over that and finish up with the arc flash categories and protective clothing. They're basically about 6 different classes of protective clothing, from class 0, which is untreated cotton, to extreme danger, where nothing is going to protect you. Okay, so here are the classes. Category 1, 2, 2-star, and 3 and 4. So the first 3 are wearing just one layer of clothing and a face shield and a hard hat. And the higher levels you're wearing over what you wear in 1 and 2, you have to wear the flash suit. So, say for category 1, you're talking arc resistant shirt, pants, or coverall with a face shield or a hood. Category 2, you also have to wear cotton underwear and shirt and pants and face shield or hood. And category 2 star, the difference in 2 star is that you wear the balaclava, which is, you can see the little white sort of head scarf that he's wearing under his hard hat and shield. It's called a balaclava. There is a type of ski mask that has that name that's made out of heavy wool, but this is made out of arc-resistant, fire-resistant cloth instead. And that will protect, for example, the back of your neck and your ears and things which may not be protected by the face shield. So then on your arc flash label, it lists exactly what you need to wear. It tells you the arc flash protection boundary that is, in this case, within 41 feet, you have to wear this clothing if there is an exposed conductor that you're going to be working on. And it gives you, okay, you have 15.6 calories per square centimeter at 36 inches. This is class 3. So with the class 3, you have to be wearing the arc suit over your protective clothing. And if we go back and look at that, class 3 and class 4, you have to wear the flame-resistant coverall and face shield or hood. For class 4, you have to wear a multi-layer flash suit. And then it also gives you the shock hazard, gives you the voltages and the limited, restricted, and prohibited approach boundaries. Oh, and it also tells you where it tells you where the label is supposed to be placed on T3 feeder breaker front door, and it also should have a date on it. I think it says 0126, 7/2007. Okay, there's a date on it. Okay, you have a date on it because after a while, things change in every plant, and you need to get new labels. And here's a typical work permit, which would be filled out before doing any work, and it tells you what work you're going to do and what the expected hazards are, and there's places for appropriate people to sign it. So that concludes my presentation. I know I've run a little bit over, but if there's any questions or discussions, please let me know, and I'll be here for, how much longer do I have, Fernando?
Yeah, so thank you very much, Peter, for this comprehensive presentation. We will proceed to questions and answers right now. As the presentation was quite long, we will stay for 5 to 10 minutes depending on the number of questions. So I suggest we start with yes, with the first question from Dominique. So I'm sending to the Q&A pod. So is arc flash analysis compulsory, and if so, is it retroactive to old installations? Thank you.
It is compulsory in the United States, and it is retroactive on old installations. I can't speak for other countries, though.
Okay, perfect. So I invite the audience to submit additional questions if you have any. Otherwise, for the time being, there are no additional questions. Okay, so I think it's been quite clear the presentation. There are no remaining questions for the time being. So I suggest we close here the session today. So thank you very much, Peter, for this interesting and comprehensive presentation. The material will be uploaded together with the webinar recording. So in the link that we present here, so you can go there and visit, play again the webinar. So I give you the floor, Peter, to conclude the session. Thank you.
You're welcome. And if anybody has any additional questions, how can they send them in?